In the previous video, the introduction to bending moments, we defined what bending moments were as reactions to bending caused by a force acting on a structural element. In this video, we're going to do some numerical analysis of bending moments. Let's start with a simple case of an ideal massless beam. That is, a beam whose weight does not contribute greatly to the reactions and is significantly less than the external loads acting on it. Here we have a 10 meter long beam that is simply supported by two supports at its ends. Let's add a load at the center of the beam, 5 meters away from support A, with a magnitude of 100 newtons. This load will exert a downward force onto the horizontal beam, so the force and the beam length vector is 90 degrees with each other. As there is a downward force of 100 newtons, the two supports must exert a reaction back up equal to the downward force. Since the supports are at the ends, they will react equally to the force and will produce a reaction equal to half the force each. That is, they will react with an upward force of 50 newtons. Recall in the shear forces video that to calculate the shear force at any point along the beam, we first cut the beam at that point and analyze the shear reactions of the beam at that cut. We add up all of the forces on the beam up to that point, starting from the left end of the beam. The shear force by the beam at that point will be its reaction to the net sum of all forces up to that point. Calculating bending moments is done in a similar way, where we cut the beam at the point of interest, look at all the forces before that point and how much bending moment each force creates about that point. The total bending moment at the point is the vector sum of all the bending moments from each force about that point. Let's start at the left end of the beam, which we take as the origin for our analysis. At this point, there is one force pointed upwards, which is a reaction from support A of 50 newtons. Recall from the introduction to bending moments video that bending moment is defined as a product of the force and the distance that the force acts from where the bending moment reaction occurs. At the origin, the force is Ra and the distance is 0, so the moment at the origin is 0. What this result tells us is that the reaction force Ra does not create a bending moment at the origin. This is expected as there is no lever distance for the force to create a moment from. Now let's move along the beam to a distance of 2 meters from the origin. We'll cut the beam here and determine what the bending moment is about this point. From the diagram we can see that the only force up to 2 meters is still Ra. As Ra points upwards, it will want to bend the beam about the cut point in a clockwise direction as shown by the green arrow in the diagram. The clockwise direction is positive in our sign convention. So the moment at the distance of 2 meters is given by Ra multiplied by 2. This gives us a value of 100 Newton meters. Moving along the beam to 4 meters now, let's cut the beam there and calculate the bending moment at 4 meters. We take the same approach and calculate the moment due to each force from the start of the beam to the point of cut. Again, we only see Ra as the only force between 0 and 4 meters. So only Ra produces a moment about 4 meters, and this gives us a value of 200 Newton meters. Now we move to the halfway point on the beam at 5 meters. Here we can see that there are two forces acting between 0 and 5 meters. They are Ra and the applied load F. Ra is 5 meters from the cut, so produces a moment equal to Ra multiplied by 5. But since F is right on the cut, its distance to the cut is 0, so it doesn't produce any moments. The bending moment at 5 meters is thus 250 Newton meters from Ra. For our next point to cut, we'll go to 7.5 meters. From here we can see two forces, Ra and the load F between 0 and 7.5 meters. Ra is at a distance of 7.5 meters from the cut, and since the applied force is at the center of the beam, then it is a distance of 2.5 meters from the cut. As F points downwards, it produces a moment about the cut in an anti-clockwise direction. Moments in the anti-clockwise direction is negative in the sign convention. So our moment equation becomes the bending moment due to Ra minus the bending moment due to F. And this gives us a value of 125 Newton meters at 7.5 meters along the beam. For our final point, we will calculate the bending moment at the end of the beam at 10 meters. Across the 10 meter length of the beam, we see three forces, RA, F, and RB. RA is at a distance of 10 meters from the cut, F is at a distance of 5 meters from the cut, and RB is right on the cut. Our equation then will have three moments in them. But since RB is right on the cut point, its distance will be 0, so it actually doesn't produce any moments. The total moment at 10 meters works out to be 0. We have now calculated the bending moments at 6 points along our beam. So let's recap these results and show them on a graph. Here, the horizontal axis represents the distance along the beam and the vertical axis represents the bending moment. At 0, the bending moment is 0. At 2 meters, the bending moment is 100 Newton meters. At 4 meters, the bending moment is 200 Newton meters. At 5 meters, the bending moment is 250 Newton meters. At 7.5 meters, the bending moment is 125 Newton meters. And finally, at 10 meters, the bending moment is 0. So the bending moment takes a profile of a triangle that starts at 0, rises linearly to peak where the load is, and then falls linearly back to 0. This triangular profile is indeed what we see when the load acts on an element that is relatively light compared to the load. An example of this is a pendant on a necklace. But while in a physical scenario, the triangle points downwards, this is considered a positive curve according to the sign convention, and the bending moment diagram is represented by a triangle in the positive upward direction. Now let's have a look at a case where our beam has a uniformly distributed load on it. This UDL could be from an external load, or it could be from its own self-weight. In this example, we're going to use a value of 10 newtons per meter. That is, for every 1 meter of the beam, there is 10 newtons of force acting down and distributed evenly over that 1 meter. So the total load along the 10 meter beam is 100 newtons. Since our supports are at the ends of the beam, each support produces a reaction equal to half of the total load. If the supports were positioned somewhere else other than the end of the beam, we'll have to calculate what the reactions are using torque or moment analysis. But since they're at the ends of the beam, we know they carry an even amount of load, which is half of the total load, or 50 newtons each. So to know what the bending stress is at any point along the beam, we do the same thing as previously, and we cut the beam at the point of interest. Then look at all the forces before the cut and calculate the bending moment due to those forces on the cut. So let's start at the beginning of the beam on the left, which is our origin. At the origin, there is one force acting at that point. This force is RA with a value of 50 newtons. But since RA is directly on our point, there is no lever distance for RA to act to create a bending moment. So the bending moment at 0 meters is 0 Newton meters. That's nice and easy. And it turns out that the bending moment at the ends of the points will always be 0. Now let's move along the beam to a distance of 2 meters from the origin. We'll cut the beam here and determine what the bending moment about this point is. From the diagram, we can see RA acting upwards 2 meters from the cut. As RA points upwards, it will want to bend the beam about the cut point in a clockwise direction as shown by the green arrow in the diagram. The clockwise direction is positive in our sign convention, so the moment due to RA at a distance of 2 meters from it is given by RA multiplied by the distance x. But at 2 meters, we also see a 2 meter section of the beam with a UDL on it. Because the beam is loaded, it will produce a force that is pointed downwards as shown by the red arrow here. The magnitude of this force is determined by multiplying the UDL with the length of the cut. As the UDL is 10 newtons per meter and the length is 2 meters, then the force due to the UDL on the 2 meter beam is 20 newtons. The force due to the distributed load is directed at the middle of the beam, as this is where its center of mass is. The distance from the center of mass to the cut point is half the length of the cut, or 1 meter. This distributed load force at a distance of 1 meter from the cut creates a bending moment that wants to rotate in the anti-clockwise direction. This anti-clockwise direction is negative according to our sign convention. So our bending moment equation now has another component due to the UDL on the 2 meter section of the beam. This bending moment is the force multiplied by half the distance of the cut. The negative sign indicates that this bending moment is in the negative anti-clockwise direction. We can now substitute the values into the equation with Ra being 50 newtons, x being 2 meters, F being 20 newtons, and half x being 1 meter. Calculating the answer gives us a bending moment of 80 newton meters. The positive answer indicates that the net bending moment at 2 meters is in the clockwise direction. This makes sense as we have a larger force in Ra acting at a further distance than F. Let's now move to 4 meters into the beam. We repeat the same process. Here we have Ra creating a positive bending moment at a distance of 4 meters from the cut, and the force of the distributed load acting halfway along the cut section to create a negative bending moment that is 2 meters from the cut. The magnitude of the load is now 40 newtons, since the UDL is 10 newtons per meter and there are 4 meters of beam. So the net bending moment at 4 meters is 120 newton meters. Now let's move to the middle of the beam and cut the beam at 5 meters and repeat the same process. Here we have Ra creating a positive bending moment at a distance of 5 meters from the cut, and the force of the distributed load acting halfway along the cut section to create a negative bending moment that is 2.5 meters from the cut. The magnitude of the load is now 50 newtons, since the UDL is 10 newton meters and there are 5 meters of beam. So the net bending moment at 5 meters is 125 newton meters. Let's keep moving along further to 7 meters. Here we have Ra creating a positive bending moment at a distance of 7 meters from the cut, and the force of the distributed load acting halfway along the cut section to create a negative bending moment that is 3.5 meters from the cut. The magnitude of the load is now 70 newtons, since the UDL is 10 newtons per meter and there are 7 meters of beam. So the net bending moment at 7 meters is 105 newton meters. Let's keep moving along further to 9 meters. Here we have Ra creating a positive bending moment at a distance of 9 meters from the cut, and the force due to the distributed load acting halfway along the cut section to create a negative bending moment that is 4.5 meters from the cut. The magnitude of the load is now 90 newtons, since the UDL is 10 newtons per meter and there are 9 meters of beam. So the net bending moment at 9 meters is 45 newton meters. Finally, we get to the end of the beam at 10 meters. Here we have Ra creating a positive bending moment at a distance of 10 meters from the cut, and the force of the distributed load acting halfway along the cut to create a negative bending moment that is 5 meters from the cut. The magnitude of the load is now 100 newtons. At 10 meters, we also see Rb, but since Rb acts directly at the cut, there is no lever distance for Rb to create a bending moment. So the bending moment due to Rb is 0. The net bending moment at 10 meters comes out to be 0. So by the time we get to the end of the beam, the positive bending moments cancel out with the negative bending moments. We have now calculated the bending moments for a number of points along our beam. Let's recap these results and show them on a graph. Here the horizontal axis represents the distance along the beam and the vertical axis represents the bending moment. At 0 meters, the bending moment is 0 newton meters. At 2 meters, the bending moment is 80 newton meters. At 4 meters, the bending moment is 120 newton meters. At 5 meters, the bending moment is 125 newton meters. At 7 meters, the bending moment is 105 newton meters. At 9 meters, the bending moment is 45 newton meters. And finally, at 10 meters, the bending moment is 0. So the bending moment takes a profile of a curve or parabola that starts at 0, rises to peak at the center, then curves back to 0. This curve is the shape that we see when structures are suspended with supports at the ends. like the steel beam bending under its own weight or the suspension's bridge. We'll see in the next video why the bending moment diagram for a distributed load is a curve and not a straight line. In summary, the bending moment at any point along the beam can be found by cutting the beam at that point and summing up all of the bending moments created by all forces from the start of the beam up to that point. The bending moment of a point force is equal to the product of the force magnitude and the distance the force acts from the cut. If the force points upwards, it will produce a clockwise or positive bending moment. If the force points downwards, it will produce an anti-clockwise or negative bending moment. If the force is uniformly distributed, then the resultant force vector is positioned halfway along the load distribution at its center of mass.